recording.
If you remember when I talked about sedimentary rocks, I divided them into the clastic rocks, which were subdivided first on size of particle, sandstone, conglomerate, and then second by composition, arkose versus greywacke versus the quartz sandstone. And then I talked about the chemical rocks, which are divided first by composition, limestone, dolostone, gypsum, and then I said they were divided secondarily by grain size. And then I didn't go any further in that. This is a mixed rock, which is a carbonate rock, which would be the equivalent of a shale that is very, very tiny particles. It's a limestone mud. So if you ever went fishing out in Florida Bay, the floor of Florida Bay is a lime mud. So that's what this was here, except it's the equivalent 500 million years ago. And that's about the age of these rocks, 500 million. You can tell that when this was laid down, there was no source of clastic rocks around here, because there is virtually no mud, no nothing in here. So this was almost clastic sediment free. The lime itself is probably mostly algal, and that algae will secrete little tiny particles of calcite in the cell and then release it when they're dead, and that's what makes the sediment. So the sediment is produced on the spot. It's not carried anywhere from it somewhere else. Very finely, what I call it, finely laminated. The beds here are extremely thin, and it's a mixture of both carbonates. There'll be layers of calcite, which is limestone, and then there'll be layers that are rich in dolomite as well. One way you can tell is that the calcite is more soluble. Well, you can tell that from the acid test. The limestone fizzes like mad. The dolomite will fizz, but you have to work at it to get it to fizz. It's not as soluble in rainwater either. So what you get when you get mixed limestone and dolomite is that the layers of dolomite, rich in dolomite, stand out in relief, because they don't dissolve away as well. And so you get this very ribbed appearance. Now, for the origin of the dolomite, I asked this question on a test actually. How does dolomite form? Accumulation of dolomite shells or magnesium-rich minerals? And the correct answer was it's a reaction of magnesium-rich brine with original limestone. The way you can tell that for sure, by the way, is that you can find seashells that you know started out as calcite, and they're replaced by dolomite, and you know these shells started out as calcite. So you presume it's like that. I think Cutler may know whether anyone has yet found primary precipitating dolomite. I suspect it has, but I'm not really sure. But certainly most of it is with the reaction with brine, because magnesium is concentrated in the ocean. As a matter of fact, if I can, remember that handout I gave you to do on the various elements and where they come from? Magnesium comes from seawater. That's where they get it. They extract it directly from seawater. That's the core. And when you concentrate seawater, the first thing that comes out is calcium carbonate. It's calcium carbonate and calcium sulfate, calcite and gypsum. Then you get sodium chloride. Then you get potassium chloride. And after that, the last few things to come out are mainly the magnesium salts. So you have to get very concentrated brine to get lots of magnesium. When you get that magnesium-rich brine and you react it with calcium carbonate, it replaces calcium by magnesium, and so you get dolomite. Okay, so where do you get that sort of a magnesium-rich brine, concentrated brine? Hot and dry. Go to the Red Sea, and you'll find that sort of process going on now. Gulf of California might be another good place to but someplace where the climate is hot and dry. So we can get an indication that a lot of this rock here was laid down in a climate that was basically hot and dry.
Like Arizona?
Well, except that the ocean is there.
Well, okay.
That's why the Red Sea is the
Okay.
best example today. It's a semi-enclosed sea that becomes very salty, and especially on the mud flats, on the tidal flats, where you get the water evaporating and actually can get salt deposition.
Yeah. But that's crazy.
That got broken up by a storm and then redeposited as jumbled pieces. So here is a weather report from 500 million years ago. There was a really nasty storm the other day. You had the crust of carbonate on the tidal flat, and this really nasty hurricane came in, and it mixed up and jumbled all those layers, part of which were already lithified, and then redeposited them at all these odd angles. So you never think that you could find a weather report still around from 500 million years ago.
Yeah.
But here it is.
Really nasty storm, though.
It was a really nasty storm. Yeah. Most of the time, it's pretty calm. Not much going on. But how long it takes to deposit these layers? Do you know, Alan?
I can't say offhand. I mean,
Yeah, this is something that people work on. How long does it take to deposit an inch of this stuff? Yeah. And it varies from place to place. I do not know what the estimates would be for here.
that could be seasonal or monthly or longer term than that. It's hard to say.
It's hard to say. Now, this is one reason why a lot of geologists tend to like to study carbonate petrology, because to study this, you go to the Bahamas or Florida Bay, places like that, that are really nice places to spend some time. Spend time at a nice resort in the Bahamas and come out with a paper out of it. On the other hand, if you want to study glacial geology, dress warm. It's not going to be vacation country. I don't really know how big an effect this has on the fields that people pick, but I suspect it may have something to do with it.
Oh yeah.
So anyway, that's beautiful, typical laminated micrite limestone dolomite. Well, let's see. Is it really limestone? Let's see. Can you see from down there?
Fizzing, yeah.
Fizzing like that.
Even I can see fizzing from way down here.
Yes.
Yeah.
I gotta get a shot of it, but you're in the way.
Wait a minute, I just planted my...
I got you.
And Rupert's soft and squishy. Pretty with layers. Vigorously.
Yep, so this is limestone, not dolomite.
Hydrochloric acid.
That'll do it, yeah.
It's not incredibly strong, but it's reasonably strong.
Yeah.
Very, very convenient.
Given to him by the chemistry department,
If I remember correctly,
but through the physics lab coordinator,
There we
me.
if I remember correctly, it's not a strong acid, but it's pretty close.
Yeah.
It's 3 molar.
Oh, okay.
You still wouldn't want to gargle with it.
Yeah, no.
Yeah, no, I grossed out some of my students. When I put it in the rock, I didn't have anything to blot it up with, so I licked it up. It's just stomach acid,
Yeah, right.
and hydrochloric is not really terrible stuff.
Yeah, it's close though. If it were hydrochloric, you'd be in trouble.
What is
Oh, yeah.
hydrochloric?
Oh, hydrofluoric.
Hydrofluoric? No.
It goes right through bone.
Or
Everything.
even sulfuric. Right. Hydrochloric is harmless as far as the only thing that's active. With all the other acids, there's something else going on.
Oh, especially fluorine. Yeah, that fluorine will tear through anything.
Yes. Okay, this, by the way, is the Elbrook Formation, Elbrook Limestone. Our next stop is also going to be Elbrook, except there you get to see some very nice solution features on a small scale. This is all karst country. This is cave country, so we do have some large-scale solution features too. But we're not going to take a cave trip today. Limestone.
It can't be gray wacky.
Now, they ain't gray wacky. What about these white streaks through here? Cutting across. First, what are they made of? Well, nope, they're limestone. Or calcite, actually. Now, this particular area has been deformed. These rocks have been tightly folded, actually. You can't see it right here. It looks as though they're pretty nearly level right here. But by and large, these rocks are deformed. And when they've been deformed, they tend to break. They do fracture. And when they fracture, you get solutions trickling through them, dissolving calcite from the limestone and redepositing it as pure calcite in these little veins. And those are sometimes called gash veins. And if you are interested in structural geology, you might look at these and study their orientation and try to figure out what you could tell about the deformation of the rocks from the orientation of the little cracks in them. That's not my specialty. I'm not a structural geologist. But other people could probably, another geologist might concentrate on that. Second, see this little line here?
Oh, yeah,
That's a strong, what do we call it? Stylolite, yes. It's pressure solution here. You've got, once you start dissolving a little bit, then water can get in there, and under pressure, it turns out calcite is slightly more soluble. So once it starts dissolving, it'll continue. And you get these fractures, and it's hard to tell how much has been dissolved out. It'll be considerably more than the fraction of an inch that it looks like. Sometimes you can tell because there'll be a fossil that'll be cut across by the stylolite, and you can see that the top of the fossil is preserved, the bottom of the fossil is preserved, and they've been pressed together and the middle of the fossil has disappeared. You can tell that much, one fossil's thickness has been dissolved out.
That break you're talking about?
Well, these are the gas fractures. The texture is pretty line here. This is over here. That's a solution feature. And I just gave you away. This is a little tiny cave. If you were a chipmunk, this would be a perfectly good cave to explore. And anyway, you can see that I put my hand down in here, and it comes out down here. Now, on occasion, this is all cave country. And it might well be that you could find a hollow that is not filled with a pond. I explained this the other day in lab when we were talking about topographic maps. Around here, you could find those enclosed hollows. At the bottom of that hollow, you'd find things like this. And that's what prevents the water from building up as a pond. It's a leaky pot. All the water goes down through the holes in the bottom and sinks down into the groundwater. Perhaps by way of some large-scale caves. And cave explorers really like to find things like this because it's an indication that there's been a lot of solution and that there is at least the potential for some good cave discovery. But this is much nicer solution features than the ones we saw at the other spot. That's why I bothered to come up here. It's close by. Okay, so we can continue on to the next one then. I think the next one may be all the way over to the base of the Blue Ridge.
Also, I'm going to put my hand in the screen.
You're going to put your hand in, slip, and then break your arm.